Okay. Now let's prove C is equivalent to what do you call D. So for that, what we need to show that if U star is the right inverse of U, then the rows of U are orthonormal. This is what that you have to show. Now if you take, for example, U star I, then I can write this as this U as star is star. In other words, you take a matrix U, conjugated transpose, and then again conjugated transpose, you return to the same matrix. This is equal to U star and identity. So that since U star is equal to U, so this must be true. And if this is true, okay, then I can write this as, say, V star V equal to identity, where V is U star actually. Okay? Where V is U star. So if I give U star name V, then this shows that V star V is identity. And what does this mean? This means that V is unitary. V is unitary. Okay? And V, by V I mean U star. And if V is unitary, okay, then the columns of V, okay, the columns of V are, the columns, okay, let's write, say, V as say, V1, column wise V2, Vn. Okay, so this is unitary. This is unitary. Okay? Where we know that what are the columns of V in the terms of U. It's not difficult. Now if V is a unitary, that means, and you know, A is equivalent to V, that means that the columns of U are orthonormal. This implies that columns of V are orthonormal. Orthonormal. That is, that if you take Vi, an arbitrary column of it, and compute a star of it, and multiply it with Vj, you're going to get delta Ij. And delta Ij is 1 when Vi star, when I is equal to j and each equal to 0. Now I am feeling, consider so if the columns of V are orthonormal, then consider V star, which is actually equal to U, which are actually equal to U. Now, what will come in V star? So these columns will become rows, and you will have their conjugates. So V1 star up to Vn star. So you will put these rows in columns, in rows. So this would be your V star. And why V star is U? Because think about it. So the V star is U star, and its star is U actually. Okay? And now my claim is that the rows of U, which are these V star, V1 star, V2 star, they are orthonormal as well. Why? Because if you take Vi star, means the ith row of it, and multiply its star with say Vj, okay, with Vj star, okay, what are you going to get? So Vi star is going to be equal to, this is going to be equal to Vi times Vj star. But this is delta Ij. So this must be also delta Ij. So what does this shows? That the columns, the rows of U are orthonormal set. Okay. The rows of U are orthonormal. Okay, they are orthonormal. So this shows the equivalence of C and D. So, okay, A and C are equivalent. So you have to be careful in equivalence actually. So I think we have shown first A and B, and then we have also shown that A and C are equivalent. Okay. So in other words, if this is true, then this is true. And if these both are true, this means that U is true. Okay? That means that U is invertible actually, because U is the left inverse and E is the right inverse. I can say that C is equivalent to E. Okay? C is equivalent to E. Because if U is invertible, this is true, and if this is true, from the equivalence of A and U, A and E, U is invertible actually. U is invertible because U star becomes the left inverse and the right inverse actually. Okay? Now let's say think about F and G. Okay, so let's think about say F and now let's think about say G and A. Why G and A are equivalent actually. So here is the case. So suppose A. Suppose A. I want to show G. So I know that U is unity matrix. And we know about the unity matrix that if you consider the transformation corresponding to the unitary matrix, this transformation is an isometry. It's an isometry. Okay, it's an isometry. Now I'm going to use, and how it is related with the matrix U, that such that if you operate U onto some x, this is equal to U multiplying U with x. Okay, so how a linear transformation and its matrix are related with each other, so they are related with each other in this manner. Okay. Now I want to show this identity. So how can I show it? So if I take Ux square and I equate it, so the Ux is equal to Tux, transformation of x square. But this Tu is an isometry, so this must be equal to what you call norm of x square, and this implies norm of Ux is equal to norm of x. Okay? And basically you can go other way around in a similar manner actually. So if you, for example, you want to do G implies A, so then you're going to say that, okay, Ux is equal to what you call norm of x. But the Ux is same as Tux. So Tux is equal to norm of x. So what does this show? That TU is an isometry. And if TU is an isometry, U is a unitary matrix. U is a unitary matrix. Okay? So this shows both sides. But the proof is not difficult. It's just a bit of working out. What I would like to use, for example, G and H. Okay. So, by the way, what is the inner product on Fn? The inner product of Fn is Rn. Fn is Rn or Cn, and the inner product on Fn or Rn in general can be written as, so if you have xy, so it's y star x actually. So take the conjugate transpose of y and multiply it with x. So this is what we like to show. So for example, let's show first f implies a. Okay. So I would like to show that U is a kind of a matrix which the norm of ux is equal to norm of x. Okay. So the given is that the norm of ux, the magnitude of say ux is equal to x. This is what is given to me. Okay? And I want to show this. By the way, showing this is equivalent to show that uy, the inner product of uy, ux is same as yx. I can rewrite this because this can be written as this and this can be written as this. This is what I would like to show actually for ux and uy. The answer is you can do it easily. Why? Because if you, for example, take this uy and ux, okay, and apply the polarization identity, so this would be equal to 1 over 4 norm of uy plus ux square minus uy minus ux square. Okay, using polarization identity, this is equal to this. I can say that this is same as 1 over 4 times of norm of ux plus y norm square minus uy minus x norm square. This is what you're going to get. And now, like, the norm of ux is equal to the magnitude of x actually for any vector x. So this must be equal to, what do you call, 1/4 of norm of x plus y minus norm of say y minus x, and this is 1. And if this is case, this is precisely equal to yx. This is precisely equal to yx. Okay, this is precisely equal to yx. By the way, you have to keep this thing in head that these norms are the norms in Rn or Cn. So these norms are in Fn. Okay, these norms are in Fn because ux is a vector in Fn. So this must be true. So we showed that if this is true, this is true. Okay, and if this is true, okay, if this identity is true, why this must be true? Just substitute y equal to x actually. So this is true for all y and x. So for h, maybe but f belongs to h. This is f implies h. For h implies h, this is really easy. Just since this identity is true for all x and y, so just take say x equal to y in this identity. So you get precisely this actually. Okay? So this kind of proves some of the basic properties of the unitary matrices. So, so we kind of justified every single part in this theorem. You can read it more. If you have questions, you may ask in Zoom session. So what does this show? That the being unitary matrix is equivalent to many things. So if your matrix is unitary, your columns are orthonormal, your rows are orthonormal, your matrix, your unitary matrix is invertible, okay? The matrix is invertible, and it's a kind of a magnitude preserving matrix, and it satisfies. So it's really an isometry actually. It's really an isometry. So it really satisfies the identities, this and this identity, which are equivalent